Hey, it's Dr. J. We're starting chapter 3 today. We'll start with 3.1, natural place to start, the introduction to integers. So just a quick review of the different number sets. We started with the natural numbers. Back in chapter 1. The natural numbers are also called counting numbers. I don't use that terminology very often, but it's definitely been used before. I like to call them caveman numbers. That's what I like to call them. Because, you know, our ancient ancestors, 10,000, 20,000, maybe even longer, could count. They might not have used these symbols that we use today, but they could definitely count. Okay, so we have the natural numbers. Notice that 0 is not a natural number. Yeah, it took a very long time for human beings to develop the concept of 0. If I start talking about that now, I'll never shut up. I do teach a course in liberal arts mathematics. It's sort of like history of math a little bit, and where I give a much more broad description of the number systems. If you're interested, you might find some of those videos on YouTube. I don't know. But needless to say, we're in an algebra course, so I'm just going to get right onto it, and then we talk about the whole numbers. I don't really know another name for the whole numbers. They're just called the whole numbers. The whole numbers are the natural numbers plus 0. Yeah, we call that whole. Obviously, it's going to keep going. 10, 11, 12, 13, 14, so on and so forth. All right, and that's pretty much where we left off. And so the idea is that the natural numbers can count objects, whole objects, 1, 2, 3. We don't have any decimals, we don't have any fractions, and we certainly don't have 0. The whole numbers give us the ability to count nothing. Yeah, so we have a symbol for nothing. Okay? And that's a really monumental idea, because once you can have a symbol for nothing, well, then what's to stop us from having a symbol for less than nothing? And we call these the integers. Zero is sort of in the middle of the integers. And we have the natural numbers on the right-hand side. And then we have their opposites on the left-hand side. You could tell who made the rules. Clearly, a right-handed person made the rules. That's why we put the opposite values, or the negative numbers, on the left-hand side. So these are the integers. So every natural number is a whole number. Yeah. Every whole number is an integer. Right? So you have all the whole numbers are also part of the integers. Another name for integers are also called the signed numbers. Again, that's a term that you might see or hear or come across in a problem, or refer to them as signed numbers. Sign comes from either a plus or a minus sign. So these are called the negatives, because they all have a negative sign. Yeah. And then these numbers are called the positives. It's like there's an invisible plus sign here. We usually omit, not always, but we usually omit the plus sign. Although if I really wanted to emphasize that it's there, I would emphasize that by putting the plus sign. And then 0 is considered neither positive nor negative. It's the only number that's neither or neither positive or negative. Here's the idea. It's the way that I often had it described. Suppose you have some sort of flat ground. Yeah, we call that 0. The ground level could be 0. And then if I dig a hole, and I make a pile of dirt, this is the hole. Yeah. The actual dirt, the quantity of the dirt is positive. I could put it on a scale, I could measure it, I could, give it a quantity, call it, 2 cubic feet of dirt or whatever you want to call it. As a positive value. It's the actual dirt. Yeah. The empty hole is negative. So that's just the idea behind what the negative numbers represent. They represent the opposite of a positive. So the opposite of a positive is called a negative. Yeah. Obviously, if this dirt was, say, positive 5, then the hole would be negative 5. In fact, you probably know about this with your bank account. Could write this as an integer. So suppose your bank account is $42 overdrawn. Write this as an integer. And I don't know if you've ever said this before, but we often say, you're in the hole. I often say it. If my bank account is overdrawn by $42, I'll say, I'm in the hole for $42. It's like you're below ground level. Ground level is 0, and you're down in the hole. And so to represent $42 as an integer, it would be negative $42. I don't really care about the dollar sign so much. Typically, we just kind of put the dollar sign off to the side. I guess you could say it this way. I don't really want you typing it this way, but you could say negative $42. This one's kind of dangerous because I don't really want you squeezing the dollar sign in there. The integer is negative 42. All right. The dollar sign is just the symbol to talk about, to represent the fact that we're talking about money. If the next day, I deposit, I receive a direct deposit, and my account now has a balance of $185 as an integer. Represent this as an integer. Well, it already is, yeah. The integer is just 185, or you could say positive 185. I'm not going to do that. I'm just going to say the positive sign is implied. So when you see your account balance and it says $185, we do not have to put the positive sign that is implied. Sometimes we draw our bank accounts vertically like this. You sort of have 0. You got negative 42. That's down in the hole. And then you have, say, a positive 185 up there. I know my graph is not to scale, but that's one way of doing it. Basically, there's only 3 things. I mean, this isn't only the 3 things, but in our class, there are 3 things. I'm using the word things very loosely. In the world that we use integers for. Number 1, money. Yeah. It is very, very difficult to buy a house without integers, right? I mean, unless you happen to have, a bag of money that has, $2 or $3 or $400,000 in it, a suitcase or a trunk full of money. Most people do not buy houses with actual money. They buy them with negatives. Yeah, we borrow the money. Yeah, we get into the hole. Yeah. I've told this story before, and then I had a student come up to me after class and go, I actually did buy a house with a big bag of money. But I mean, it's very, very rare to do that. The second thing is temperature. We already discussed money, but we have temperature. We'll talk about that in a minute. For example, the temperature, it doesn't happen here in the desert, but the temperature could go below 0, and we could have negative temperatures. And the third thing is elevation. In other words, how high are we? Are we above the surface of the earth or above sea level? Yeah. Or are we below sea level? Those are the 3 basic things in this class that we'll use integers for. Okay. There are more, but I mean, I'm not going to make the list, 20 things and say, oh, there's 20 things that we need to know. There are basically 3 things that we're going to use integers for. We've already talked a little bit about money. Let's talk a little bit about temperature. So we talk about temperature. If you have Celsius, also called centigrade, and we have a degree symbol. So we call this degrees Celsius. It's the degree symbol. 0 is freezing. 0 degrees is freezing. Right? And then the positives, so you can imagine a thermometer or something like this, You've got a thermometer like this, and we're doing degrees Celsius. So 0 would be freezing. Of course, that's water. We're talking about the temperature at which water freezes. 100 degrees would be boiling. Okay. And then anything down here, this would just be below freezing. I just picked negative 20, for example, but any negative number would be considered below freezing. So that would be the Celsius scale. Positives are above freezing, and negative is below freezing. Fahrenheit's a little bit different. I always feel like I'm spelling it wrong, but I'm just going to use F for Fahrenheit. Fahrenheit's a little bit different. It's the same diagram, actually. Yeah, I could imagine a thermometer. It could technically go to negative infinity, but I'm not going to teach physics today. But in physics, it turns out there is an absolute zero. It's, very, very cold. It's, 300 and something degrees below zero. I'm not really going to go there, but so I'm just making it look like a thermometer. 0 degrees freezing is now 32 degrees in Fahrenheit. But these are the same temperature. They are the exact same temperature. We're just using a different scale called Fahrenheit. Later in the course, not in this particular lesson, but in the course, or later in the semester, we will go back and forth. I'm doing a whole chapter later in the semester. It's I think it's chapter 6 or something, where we convert back and forth between Celsius and Fahrenheit. I'm not really going to do that today. Okay. So the weird thing about Fahrenheit is 32 is the freezing. And so 0 degrees is actually below freezing. Yeah. And then negatives would be, I don't know. We'll just do something like that. Negative 40 degrees is negative 40 degrees below 0. But it's actually 72 degrees below freezing. All right, so the negatives in Fahrenheit are much, much lower than the negatives are in Celsius. A neat little fun fact, though, negative 40, fun fact, and I will demonstrate this later in the course, of course, but I just can't resist saying it. Negative 40 is the same in both. Negative 40 is the only temperature that is exactly the same exact temperature in both scales. So if you were to take a thermometer down to, Antarctica or maybe up to the North Pole or something and measure it using Fahrenheit, it might come out to be negative 40. And I'm just saying that because that's that magic temperature. And then if you do it for Celsius, negative 40 is, in fact, the same temperature. It's the only one that's the same. Every other temperature would be different. A little fun fact about water. Water boils at 100 degrees in the positives. Over here in the Fahrenheit, 100 degrees is actually 212 degrees for boiling in Fahrenheit. So the scales are quite different. And we're going to learn to go back and forth at some point in this semester. Today, I just want to talk about the positives and the negatives. And then finally, elevation. With respect to sea level. So we would imagine that the sea or the ocean is 0. Yeah. So there's 0. Yeah. Positive would be something above sea level. Trying to draw a plane. That's supposed to be a plane. I don't know. So the plane is flying. I don't know what a plane looks like. So the plane is flying, I don't know, 10,000 feet or something. That's positive. But maybe, a scuba diver don't know if that's a scuba diver or not. I was trying to draw fins. I don't know why I'm spending so much time on the drawing. I don't know, maybe. All right, enough of that. So there's your scuba diver. It's terrible, isn't it? All right, the more I try to make it look nice, the worse it gets. So the scuba diver would be something like, I don't know, negative 110 feet or something like that. So that's negative. Yeah, because it's below the sea level. And then if something is just sitting on the sea level, like a boat, yeah, that's a boat. Yeah. Now, again, I'm not counting the actual height of the boat. I'm talking about the surface of the boat sits at 0 feet. Or maybe I shouldn't use the word sits. I'll say floats. 0 feet. So those are the three basic ideas behind why we use integers and how we use integers. In this introductory section, I'm really just saying this to sort of break the ice a little bit or break the surface, to be not so punny. As we get deeper into the lesson, I'm going to actually start giving you word problems. You know, a plane is flying at such and such feet, and a diver is down at another feet, and blah, blah, blah. And I ask you some questions about you know, how many feet apart they might be, or what's the distance between them, or you know, what's the difference between them, or something like that. Now, although we often think of integers vertically in terms of life, you know, up and down and high and low and things like that, mathematically, we use a number line. Horizontally in order to make our calculations and things like that. So here is our horizontal number line. Positives are on the right, negatives are on the left. And 0 is in the middle. I was having some technical difficulties there. I got the camera set better now. Okay. So typically in this class, until we start getting into, you know, more complicated graphs and things like that, we're always going to consider the number line horizontal, and we're going to mark off the integers 1, 2, 3, 4, 5, etc., etc. And then the negatives. Now, for the negatives, you do have to put symbols. Okay. And so let's do an example using the number line. On the number line, plot all integers that are at least -3 and less than 5. Okay, so at least means including that number. So I'm going to put a dot at -3. And remember, at least means greater than. Or equal to. Greater than or equal to. So we're going to plot all the integers that are greater than, which means to the right. Greater than means to the right of. Yeah. So we are going to plot all of the points that lie to the right of -3. Only the integers. I know my 0 is kind of funky here. Let me fix that. There we go. They should be equally spaced, at least relatively. Now we got to be careful. Less than does not include the number 5. So we're going to stop at 4. So these are all the integers that are at least -3 and less than 5. Okay. So just to be clear, we say A is greater than B if A lies to the right of B. We say A is less than B if A lies to the left of B. So if A lies on the left and B lies on the right, we say that A is less. If A lies on the right and B lies on the left, we say that A is greater. Okay. It's pretty easy to remember. Look, great, right, less, left. That's really done intentionally so that we, you can just immediately know. Greater, okay, go to the right. Yeah. I know it advantages right-handed people, but it turns out that most people are right-handed. So for all you left-handed people out there, you've probably learned to adapt already to a world that's not left-handed, and math is really going to be no different. So let's try another one of these. Plot all integers that are greater than -2 and at most 4. All right. So greater than -2, you have to actually be more than -2, not including -2. So it has to be greater than -2. It has to lie to the right of -2, not actually equal to. Yeah. So plot everybody that's to the right of -2. They have to be integers. And at most 4. At most means less than. So to the left or equal to 4. So all of these dots are to the left, less than 4. Or equal to 4, so actually including the dot at 4. Okay, I'm done with the number line for now. We'll come back to it in the next couple problems. I will mention that even when I'm not drawing the number line is always there. Okay, you can think of it as vertically or you can think of it as horizontally, but typically in the real world, life, math, bank accounts, temperature, we draw them vertically. But when we're actually solving an equation or something like that, we typically write it horizontally. It takes up less space if you do it horizontally. Okay, so let's just talk a little bit about inequalities. So we have inequalities. For now, we're going to say less than or greater than, and then we have equality, which is equal to. Okay, and then if you put these two together, it's less than or equal to. And if you put these two together, it becomes greater than or equal to. We sometimes refer to these as open inequalities. It means it does not include the number that we're talking about. And we often refer to these as closed inequalities because it includes the equality, the fact that it used to be equal. Now, I'm old enough to remember, back in the 70s and the 80s, we used to write it like this. We actually would put two lines underneath it there. Sometime, I don't know, around the 1980s, 1990s, we stopped doing that. Or it just became out of date to do that anymore. So it kind of means like these two things have kind of married together and become one symbol. I'm going to focus on these three symbols now. We'll talk about these later. All right, we're going to do these now. Less than, greater than, and equality. So example 4. Insert a less than, a greater than, or an equality to make the statement true. I want to make one thing absolutely clear. These blanks are literally just blanks. They do not mean, so in other words, if I put an inequality here, I do not mean less than or equal to. It can be a little bit confusing. So maybe what I'll do is after I complete the problem, I'll probably delete the blank. Right? Another way to do it is just to make the blank like a box here. So I'm literally just filling in the box so as not to confuse you with the extra lines, because I know it can be confusing. Okay. Now remember, a number is greater if it lies to the right, and it's less if it lies to the left. So we've got -7, -5. -5 lies to the right of -7, so -5 is greater. I think about it in terms of money. I would rather owe you $5 than owe you $7. Yeah, so which is better? Greater is kind of like better. Yeah. Okay. You could also say that -7 is less than -5. You could say that, but typically we read it from left to right. So -5 is greater than -7, although you can say it either way. All right, we got -12. Oh, by the way, 0 is like way over here. Yeah. So -12, -2, -2 lies to the right of -12, so -2 is greater. None of these are going to be equal. I give you the option, even though it's probably not going to be used this time. You got 0, you got -6, 0 lies to the right of -6, so 0 is greater. By the way, you just might as well memorize this. 0 is always greater than every negative number. Right? In other words, it's better to have nothing. It's greater to have nothing than it is to owe 6 or 6 whatever million or 6,000 or it could just be 6. You also might as well memorize this. Every positive number is automatically greater than any negative number. So if you're given a positive number and a negative number, it doesn't even matter what the numbers are. The positive number is always on the right. Okay. So none of these were equal. A negative sign can also be read as the word opposite. I think that was 4. I think this is 5, but I'm terrible at counting. Find the opposite of each number. Or I like to call them integers now. All right. So the opposite So this is the opposite of 50. So we literally read this as the opposite of 50. Yeah. How about this one? The opposite of -20 is 20. Sometimes we write it like this. So this is the expression, and this is the result. So I say, the opposite of -20. The opposite of -20 is the equal sign. So this reads, the opposite of -20 is 20. And then I'll make an important note. The opposite of 0 is 0. In other words, there's no such thing as -0. Yeah. The opposite of 0 is 0. Or sometimes we write it this way. The parentheses are not really required in these examples here, but down here, the parentheses are important. Yeah. You might have heard the expression 2 negatives make a positive. Yeah, it's a dangerous expression, but it is in fact true in this particular case. Okay, evaluate the following. I will mention a little bit about terminology. Sometimes I will say evaluate. Other times I will say simplify. Those words mean the same thing in mathematics. Now, you could just do these without even reading or thinking or even talking, but I recommend, especially in this class, talk through everything. Make sure that you're reading it as if it were a sentence. So this literally reads the opposite of 12. It's really going to help especially when we get to the word problems, that you know how to read mathematics carefully. Yeah, so sometimes we think of parentheses as the word of. Yeah. So the opposite of 12 is, that's that equal sign, is, the opposite of 12 is negative 12. Done. So let's read this one. The opposite of negative 12 is positive 12. The opposite of negative 12. Remember, opposites and negative signs are the same symbol. All right. Now, some people might have proposed early on, why don't we just make one symbol for the word opposite and one symbol for the word negative, and that might make things a little bit easier. You could certainly do that, but then at some point those two symbols would essentially become the same symbol anyway, because opposites and negatives mean the same thing. So there's no need to have two different symbols for them. Even if you think it might make things easier, those two symbols would just morph together into the same symbol ultimately. So now we have more than one opposite. We just count the number of opposites. So if there's an odd number of opposites, that will be a negative. Yeah, it's the opposite of the opposite of the opposite. Yeah. So it's like you've gone backwards 3 times. Yeah, well, now you're right back where you started. It's like you went down, up, down. Yeah. All right, here we got 4 opposites. So that's an even number of opposites. That will be positive. All right, this is like you went down, up, down, up. Yeah, down, up, and so the final answer is up. I mean, if you're thinking of positives and negatives as going up and down. If you're thinking of positives and negatives as going left and right, then it's like saying left, right, right. Yeah, and so the final answer is right, because there's 4 opposites. Next, we're going to talk about variable expressions. Just kind of adding on to this concept with variables now. Notice I still use the same terminology. For this one, I'm just going to do 2 parts. So again, evaluate means simplify, or it means find the value, or if you like to use just everyday language, it means plug in. Yeah. Although plug in is not really a mathematical term. The mathematical term is evaluate. Now, I want you to be very careful here. All right, and I know you're not going to want to be careful. It's probably easier not to be careful, just to do it, right? But I'm trying to plant a seed here so that eventually you can harvest this. And so if we're not careful now, we're just going to end up with a whole mess. So watch what I do. I remove the variable and replace it with parentheses. Okay. So that is the end. Notice that I keep the negative sign here. Keep the negative sign here. Just remove the letter. And now plug in the -8 into the parentheses. and then do the math. The opposite of negative 8 is positive 8. If you skip this step, you've got about a 50-50 chance of getting it right, which means you might as well just be flipping a coin. And if it's heads, then you'll get it right, and if it's tails, you'll get it wrong. Right? So, I mean, if you're happy with a 50-50 chance, then certainly you could skip that step. But ultimately, I don't know about you, but if you're flipping a coin on every single one of these problems and you end up with 50%, unfortunately in my class, 50% is failing. So I don't think you should be happy with 50%. 60 or 70% would be okay, but 50, no, no, no. All right, so same idea here. We're going to remove the variable and replace it with a set of parentheses. So you're going to have to use an extra set of parentheses. All right, ones that were not there originally. Keep the negative signs here. And then now plug in your negative 8. Now you have opposite of the opposite of the opposite. That's 3 opposites, so that's going to be negative 8. Okay, moving right along. That's the idea of integers and opposites and evaluating with or without variables. Basically the same problem, just one of them has a variable, the other one doesn't have a variable. Next, we're going to talk about absolute value. Absolute value looks like a pair of vertical bars. We call these absolute value bars. Absolute value bars, or absolute value symbols. Most people just refer to them as bars. Okay. You got to be careful that they don't look like ones. Right? Some people just write their ones like that, and then you draw your absolute value like that, and it's very hard. Imagine if you're doing the absolute value of 11, it would look very confusing. So we try to make them look very stiff and tall, taller than the numbers that are around them, so they don't confuse them with other numbers. So the absolute value of n is equal to the distance on the number line from n to 0. All right. So here's n. You think of n as any integer. In the next chapter, we're going to expand this concept to include decimals and fractions. But in chapter 3, it'll always be an integer. And then I want to know this distance here. And that distance is the absolute value of n. So for example, if n is 5, so 1, 2, 3, 4, 5, then the absolute value of n is the absolute value of 5, which is just 5. Now we need to be careful with this because sometimes when you see the letter n, you think positive, yeah, because you don't see a sign, and from everything that I've just been explaining, if you don't see a sign, you might assume it's positive. That's not true for variables. So for variables, I guess I'll switch back to, if n lies to the left of 0, we still call it n. And so this distance, we're not going to call it the absolute value of negative n. We're going to call it the absolute value of n. So in this case, if n is negative 5, so 1, 2, 3, 4, 5 right here, the distance, we're not going to say negative n. We're still going to say n, but we're going to replace n with negative 5. And the distance is still 5. So in other words, distance is always positive, or it's at least non-negative. Zero is a special case. It's the only number that is its own opposite, and it's also its own absolute value. The absolute value of 0 is 0. Okay, so that is the idea of absolute value. If it's on the left, the distance is still positive. Yeah, because we're just talking about how far is it. Imagine if you got in your car and you drove from negative 5 all the way to 0, and you looked at the mileage on your car odometer, it would still say 5, or 5 whatever, miles, probably miles. Yeah. And then same thing over here. If you're on this side of 0 and you drive from 5 to 0, the mileage is still 0. So these have the same mileage. We use a variable to represent a negative number. We do not call it a negative variable. We just use the positive or the symbol n to mean it's negative because it happens to be on the left-hand side. Let's do an example. Plot all integers with absolute value 8 on the number line. Basically a free answer. 1, 2, 3, 4, 5, 6, 7, 8. So the absolute value of 8 is 8. And then over here, 1, 2, 3, 4, 5, 6, 7, negative 8. The absolute value of negative 8 is still 8. All right. I guess I can leave this up here. Example 9. Evaluate for n equals negative 3, the absolute value of n. It's kind of like what I just did here on the number line, but instead of using 8, I'm using negative 3. So I'm going to replace n with negative 3. So n becomes negative 3. And now the distance is positive 3. So you just get positive 3. Sometimes we say when instead of for. It means the same thing. In this example, I'm trying to show you the difference between parentheses and absolute values. They do not mean the same thing. There's a phrase in mathematics that is sometimes true, but not always true. And one of those phrases is two negatives make a positive. We are replacing n with -6. Now, since the parentheses are already there, I don't need to add in a set of parentheses, so they're already there. So this is the case where two negatives do, in fact, make a positive. Yeah, that is true, because it's a parenthesis. It's a set of parentheses. However, in this example, if I'm replacing n with -6, this is where saying two negatives make a positive is actually incorrect. Two negatives do not make a positive here. The absolute value, you have to do this first. So simplify the absolute value first. So what is the absolute value of -6? That becomes 6, and then bring down the negative, and you get -6. So even though there are two negative signs, the result is still negative. It is not positive. So if you grew up or learned in other classes or just learned by experience in life that two negatives make a positive, I would like you to add one additional word to that, and this will help you in all of your math classes. Just say this: two negatives make a positive sometimes. Yeah, sometimes. See? Two negatives make a positive, but not all the time. Yeah, see? Two negatives did not make a positive. Let's go back to the inequalities. Insert the proper symbol. Oh, so these are the blank right here. So here's my blank here that I want you to insert the proper symbol for. All right, now most of these you can do with mental math, but just to make sure that you put the symbol in the right way, let's go ahead and do the math and then evaluate what it is. So we have the absolute value of 2. That's 2, and then bring down the negative sign. Over here, you have the opposite of -2, which is 2. And then when you take the absolute value, it becomes 2. Okay, so who is greater? 2 or negative 2? 2 is greater than negative 2, so it's greater. Okay. Here we have the absolute value of negative 4. Do that first. You get 4. Then bring down the negative sign. So you have negative 4 compared to negative 4. This one's already done. So those are equal. Negative 4 is equal to negative 4. Finally, you have negative, the negative, which is positive, because those are parentheses. That's positive 3. And then you're taking the absolute value of positive 3. That's 3. So this side represents 3. Oh, I forgot there's a missing parenthesis here. In this one, you have negative, negative, which becomes a positive. Then you bring down the outside negative. The absolute value of 3 is 3, but you bring down the negative, so this one equals negative 3. So which one's larger? 3 is larger than negative 3, so the inequality goes that direction. I guess you could draw these on the number line if you really had to, but again, I mentioned this earlier. The number line is there the whole time. Whether you draw it is really up to you. And finally, we're going to end this section with some simplifications. Also known as evaluations. Okay, so how about this one? And how about this one? I don't know how to do it, really. I don't really know how to do it. Now, make sure you follow the order of operations. Remember with the, please excuse my dear Aunt Sally, or the PEMDAS order of operations, absolute value goes in the very first category. It counts, even though it's not a parenthesis, in the order it counts as a parenthesis. Which is one of the reasons why in recent years, and our book doesn't do this, our book is still using the old-fashioned way, we often replace P with the letter G. G just stands for any grouping symbol. In particular, absolute value is a type of grouping symbol. In other words, we're grouping these together. So the absolute value of negative 7 is 7. Bring down this negative sign. And then the absolute value of 4 is 4. And then simplify the result. 7 minus 4 is 3. All right. Same thing here. Simplify the absolute value of negative 5. That's 5. Bring down the plus sign. Work from the inside towards the outside. So that'll be 6. Absolute value of 6 is just 6. And then 5 plus 6 is 11. There you go. So that concludes the introduction to integers. I'd say the two main takeaways from this lesson are opposites and absolute values, if I were to give it a subtitle. That's what the introduction is really teaching us about. In my next episode, I will be talking about addition. And so I will see you next time. Until we meet again, this is Dr. Jordan. I'll see you on the internet.